So in this first section, I'm going to spend a few minutes discussing the difference between artificial intelligence, neural networks, and machine learning. Now, the reason we need some topics to you. Now, I have very horrible handwriting. I'm not artistic whatsoever. Programming is definitely more of my thing than, drawing and doing diagrams and stuff. But I'm going to try my best, and this is just the way that I find I can convey information the best to you guys. So anyways, let's get started and discuss the first topic here, which is artificial intelligence. Now, artificial intelligence is a huge hype nowadays, and it's funny because a lot of people actually don't know what this means, or they try to tell people that what they've created is not artificial intelligence, when in reality it actually is. Now, the kind of formal definition of AI, and I'm just going to read it off of my slide here to make sure that I'm not messing this up, is the effort to automate intellectual tasks normally performed by humans. Now, that's a fairly vague definition, right? What is considered an intellectual task? And really, that doesn't help us too much. So what I'm going to do is bring us back to when AI was first created to kind of explain to you how AI has evolved and what it really started out being. So back in 1950, there was kind of the question being asked by scientists and researchers, can computers think? Can we get them to figure things out? Can we get away from just hard coding and, can we get a computer to think? Can it do its own thing? So that was kind of the question that was asked, and that's when the term artificial intelligence was kind of coined and created. Now, back then, AI was simply a predefined set of rules. So if you're thinking about an AI for maybe like tic-tac-toe or an AI for chess, all they would have had back then is predefined rules that humans had come up with and typed into the computer in code, and the computer would simply execute those set of rules and follow those instructions. So there was no deep learning, machine learning, crazy algorithms happening. It was simply, if you wanted the computer to do something, you would have to tell it beforehand, say you're in this position and this happens, do this. And that's what AI was. And very good AI was simply just a very good set of rules, or a ton of different rules that humans had implemented into some program. You could have AI programs that are stretching, 500,000 lines of code just with tons and tons and tons of different rules that have been created for that AI. So just be aware that AI does not necessarily mean anything crazy complex or super complicated, but essentially if you're trying to simulate some intellectual task like playing a game that a human would do with a computer, that is considered AI. So even a very basic artificial intelligence for a tic-tac-toe game where it plays against you, that is still considered AI. And if we think of something like Pac-Man, right, where we have, our little ghost, and this will be my rough sketch of a ghost, and we have our Pac-Man guy who will just be this, well, would we consider this ghost AI? What it does is it attempts to find and kind of simulate how it would get to Pac-Man, right? And the way this works is just using a very basic pathfinding algorithm. This is nothing to do with deep learning or machine learning or anything crazy, but this is still considered artificial intelligence. The computer is figuring out how it can kind of play and do something by following an algorithm. So we don't necessarily need to have anything crazy, stupid complex to be considered AI. It simply needs to just be simulating some intellectual human behavior. That's kind of the definition of artificial intelligence. Now, obviously today, AI has evolved into a much more complex field where we now have machine learning and deep learning and all these other techniques, which is what we're going to talk about now. So what I want to start by doing is just drawing a circle here, and I want to label this circle and say AI like that. So this is going to define AI because everything I'm about to put inside of here is considered artificial intelligence. So now let's get into machine learning. So what I'm going to do is draw another circle inside of here, and we're going to label this circle ML for machine learning. Now notice I put this inside of the artificial intelligence circle. This is because machine learning is a part of artificial intelligence. Now, what is machine learning? Well, what we talked about previously was kind of the idea that AI used to just be a predefined set of rules, right? Where what would happen is we would feed some data, we would go through the rules and then analyze the data with the rules, and then we'd spit out some output, which would be, what we're going to do. So in the classic example of chess, say we're in check, well, we pass that board information to the computer, it looks at its sets of rules, it determines we're in check, and then it moves us somewhere else. Now, what is machine learning in contrast to that? Well, machine learning is kind of the first field that's actually figuring out the rules for us. So rather than us hard coding the rules into the computer, what machine learning attempts to do is take the data and take what the output should be and figure out the rules for us. So you'll often hear that, machine learning requires a lot of data and you need a ton of examples and, input data to really train a good model. Well, the reason for that is because the way that machine learning works is it generates the rules for us. We give it some input data, we give it what the output data should be, and then it looks at that information and figures out what rules can we generate so that when we look at new data, we can have the best possible output for that. Now, that's also why a lot of the times machine learning models do not have 100% accuracy, which means that they may not necessarily get the correct answer every single time. And our goal when we create machine learning models is to raise our accuracy as high as possible, which means it's going to make the fewest mistakes possible. Because just like a human, our machine learning covered AI and machine learning, those two layers together. Now in neural networks, and it then goes to another layer where it's firing in your brain, don't know use it. Final is what we call our feature. Look at midterm 1 and final grade. Whenever we want to make a new prediction, we need to have that information to do so. Now, what's highlighted in the table is that output information going and about the importance of it. So the reason why data is so important is this is we're trying to come up with rules for a data set. We have some input information, we have some output information or some features and some labels. We can give that to a model and tell it to start training, and what it will do is come up with rules such that we can just give some features to the model in the future, and then it should be able to give us a pretty good estimate of what the output should be. So when we're training, we have a set of training data, and that is data where we have all of the features and all of the labels. So we have all of this information. Then when we're going to test the model or use the model later on, we would not have this midterm 2 information. We wouldn't pass this to the model. We would just pass our features, which is midterm 1 and final, and then we would get the output of midterm 2. So I hope that makes sense. That just means data is extremely important. If we're feeding incorrect data or data that we shouldn't be using to the model, that could definitely result in a lot of mistakes. And if we have incorrect output information or incorrect input information, that is going to cause a lot of mistakes as well, because that is essentially what the model is using to learn and to kind of develop and figure out what it's going to do with new input information. So anyways, that is enough of data. Now let's talk about the different types of machine learning. Now, what is a tensor? Now, tensor just immediately seems kind of like a complicated name. You're like, all right, tensor, like this is confusing, but what is it? Well, obviously this is going to be a primary aspect. Now, what is a tensor? Now, tensor just immediately seems kind of like a complex kind of vector calculus. You should vector can have actually what that means. We talked about in the things, and if you sum Tim. Now, if I can't convert non-square us here and have a look, reshape it for us through this if you want to understand some more in depth on how that works. And the source for this is So welcome to module 3 of this course. Now what we're going to be doing in this module is learning the core machine learning algorithms that come with TensorFlow. Now these algorithms are not specific to TensorFlow, but they are used within there, and we'll use some tools from TensorFlow to kind of implement them. But essentially these are the building blocks before moving on to things like neural networks and more advanced machine learning techniques. You really need to understand how these work because they're kind of used in a lot of different techniques and combined together. And what I'm about to show you is actually very powerful if you use it in the right way. A lot of what machine learning actually is, and a lot of the machine learning algorithms and implementations in businesses and applications and stuff like that, actually just use pretty basic models. Because these models are capable of actually doing, very powerful things. And when you're not dealing with anything that's crazy complicated, you just need some basic machine learning, some basic classification, you can use these kind of fundamental core learning algorithms. Now, the first one we're going to go through is linear regression, but we will cover classification, clustering, and hidden Markov models. And those are kind of going to give us a good spread of the different core algorithms. Now, there is a ton, like thousands of different machine learning algorithms. These are kind of the main categories that you'll cover, but within these categories, there is more specific algorithms that you can get into. I just feel like I need to mention that because I know a lot of you will have maybe seen some different ways of doing things, and this course might show you, a different perspective on that. So let me just quickly talk about how I'm going to go through this. It's very similar to before. I have this notebook, as I've kind of talked about. There is a link in the description. I would recommend that you guys hit that and follow along with what I'm doing and read through the notebook. But I will just be going through the notebook, and then occasionally what I will actually do, oops, I need to open this up here, is go to this kind of untitled tab I have here and write some code in here. It's because most of what I'm going to do is just copy code over into here so we can see it all in kind of one block, and then we'll be good to go. And the last note before we really get into it, and I'm sorry I'm talking a lot, but it is important to make you guys aware of this, you're going to see that we use a lot of complicated syntax throughout this kind of series and the rest of the course in general. I just want to make it extremely clear that you should not have to memorize or even feel obligated to memorize any of the syntax that you see. Everything that you see here, I personally don't even have memorized. There's a lot of what's in here that I can't just come up with on the top of my head. When we're dealing with kind of a library and module so big that, like TensorFlow, it's hard to memorize all those different components. So just make sure you understand what's happening, but you don't need to memorize it. If you're ever going to need to use any of these tools, you're going to look them up. You're going to see what it is. You're going to be like, okay, I've used this before. You're going to understand it, and then you can go ahead and, copy that code in and use it in whatever way you need to. You don't need to memorize anything that we do here. All right, so let's go ahead and get started with linear regression. So what is linear regression? Well, it's one of the most basic forms of machine learning, and essentially what we try to do is have a linear correspondence between data points. So I'm just going to scroll down here to a good example. So what I've done is used matplotlib just to plot a little graph here, so we can see this one right here. And essentially, this is kind of our data set. This is what we'll call our data set. And what we want to do is use linear regression to come up with a model that can give us some good predictions for our data points. So in this instance, maybe what we want to do is, given some X value for a data point, we want to predict the Y value. Now in this case, we can see there is kind of some correspondence linearly for these data points. Now what that means is we can draw something called a line of best fit through these data points that can kind of accurately classify them, if that makes any sense. So I'm going to scroll down here and look at what our line of best fit for this data set actually is. We can see this blue line, it pretty much, it is the perfect line of best fit for this data set. And using this line, we can actually predict future values in our data set. So essentially, linear regression is used when you have data points that correlate in kind of a linear fashion. Now, this is a very basic example because we're doing this in 2 dimensions with X and Y, but oftentimes what you'll have is you'll have data points that have, 8 or 9 kind of input values. So that gives us, a 9-dimensional kind of data set. And what we'll do is predict one of the different values. So in the instance where we were talking about students before, maybe we have a student's, midterm grade and their second midterm grade, and then we want to predict their final grade. What we could do is use linear regression to do that, where our kind of input values are going to be the 2 midterm grades, and the output value is going to be that final grade that we're looking to predict. So if we were to plot that, we would plot that on a 3-dimensional graph, and we would draw a 3-dimensional line that would represent the line of best fit for that data set. Now, for any of you that don't know what line of best fit stands for, it says line, or this is just the definition I got from this website here. Line of best fit refers to a line through a scatter plot of data points that best expresses the relationship between those points. So exactly what I've kind of been trying to explain. When we have data that correlates linearly, and I always butcher that word, what we can do is draw a line through it, and then we can use that line to predict new data points. Because if that line is good, it's a good line of best fit for the data set, then hopefully we would assume that we can just, pick some point, find where it would be on that line, and that'll be kind of our predicted value. So I'm going to go into an example now where I start drawing and going into a little bit of math so we understand how this works on a deeper level, but that should give you a surface level understanding. So actually I'll leave this up because I was messing with this beforehand. This is kind of a data set that I've drawn on here. So we have our X and we have our Y and we have our line of best fit. Now what I want to do is I want to use this line of best fit to predict a new data point. So all these red data points are ones that we've trained our model with. They're information that we gave to the model so that it could create this line of best fit, because essentially all linear regression really does is look at all of these data points and create a line of best fit for them. That's all it does. It's pretty, I don't know the word for it. It's pretty easy to actually do this. This algorithm is not that complicated. It's not that advanced. And that's why we start with it here, because it just makes sense to explain. So I hope that a lot of you would know in 2 dimensions, a line can be defined as follows. So with the equation, y equals mx plus b. Now b stands for the y-intercept, which means somewhere on this line. So essentially where the line starts. So in this instance, our b value is going to be right here. So this is going to be b, because that is the y-intercept. So we could say that that's like, maybe, you know, we go on, we'll do this. We'll say this is like 1, 2, 3. We might say b is something like 0.4, right? So I could just pencil that in. So 0.4. And then what is m, x, and y? Well, x and y stand for the coordinates of this data point. So this would have, you know, some x, y value. In this case, we might call it, you know, something like, what do we want to say? 2, 2.7. That might be the value of this data point. So that's our x and y. And then our m stands for the slope, which is probably the most important part. Now, slope simply defines the steepness of this line of best fit that we've done here. Now, the way we calculate slope is using rise over run. Now, rise over run essentially just means how much we went up versus how much we went across. So if you want to calculate the slope of a line, what you can actually do is just draw a triangle. So a right angled triangle anywhere on the line. So just pick 2 data points. And what you can do is calculate this distance and this distance. And then you can simply divide the distance up by the distance across, and that gives you the slope. Now, I'm not going to go too far into slope because I feel like you guys probably understand what that is, but let's just pick some values for this line, and I want to actually show you some real examples of math and how we're going to do this. So let's say that our linear regression algorithm, you know, comes up with this line. I'm not going to discuss really how it does that, although it just pretty much looks at all these data points and finds a line that, you know, it splits these data points evenly. So essentially, you want to be as close to every data point as possible, and you want to have as many data points, you want to have like the same amount of data points on the left side and the right side of the line. So in this example, we have, you know, a data point on the left, a data point on the left. We have 2 that are pretty much on the line, and then we have 2 that are on the right. So this is a pretty good line of best fit because all of the points are very close to the line and they split them evenly. So that's kind of how you come up with the line of best fit. So let's say that the equation for this line is something like y equals, let's just give it 1.5 and x plus, and let's say that value is just 0.5 to make it easy. So this is going to be the equation of our line. Now notice that x and y don't have a value. That's because we need to give the value to come up with one of the other ones. So what we can do is we can say if we have either the y value or we have the x value of some point, and we want to figure out, you know, where it is on the line, what we can do is just feed one in, do a calculation, and that will actually give us the other value. So in this instance, let's say that, you know, I'm trying to predict something and I'm given the fact that x equals 2. I know that x equals 2, and I want to figure out what y would be if x equals 2. Well, I can use this line to do so. So what I would do is I'm going to say y, and I would say, okay, so if you're telling me x is 2.7 or something, I could plug that in, just rearrange the numbers in this equation just to hopefully clear some things up, because it is important to kind of get a grasp and perspective using like all the dimensions here. But it is hard because drawing in 3 dimensions on a 2-dimensional screen, the scale of this. Now notice that this line is in 3 dimensions, right? This is going to cross our, I guess this is our x, y, and z axes. So we have a 3-dimensional line. Now the equation for this line is a little bit more complicated. I'm not going to talk about exactly what it is, but essentially what we do is we make this line and then we say, okay, what value do I want to predict? Do I want to predict y, x, or z? Now, so long as I have 2 values, so 2 values, I can always predict the other one. So if I have, you know, the x, y of a data point, that will give me the z. And if I have the z, y, that will give me the x. So long as you have, you know, all of the data points line and we're using that to predict. Again, just understand that we use linear, we're, you know, that kind of student predicting, and they would finish with a lower grade. And you would assume if they have a higher grade, they would finish with a higher grade. Now you could also do something like predicting, you know, future life expectancy. Now this is kind of a darker example, but essentially what you could think of here is if someone is older, they are expected to live, you know, like not as long. Or you could look at health conditions if someone is in lower. So that's an example of something that is correlated linearly. When you think versus how much one goes down is exactly what our algorithm figures out for us. We just need to know to pick linear regression when we think things are going to be correlated in that sense. Okay, so that is enough of the explanation of linear regression. Now we're going to get into actually coding and creating a model, but we first need to talk about the data set that we're going to use in the example we're going to kind of illustrate linear regression with. Okay, so I'm here and I'm back in the notebook. Now these are the imports we need to start with to actually start programming and getting some stuff done. Now the first thing we need to do is actually install sklearn. Now even if you're in a notebook, you actually need to do this because for some reason it doesn't come by default with the notebook. So to do this, we just did an exclamation point, pip install -q sklearn. Now, if you're going to be working on your own machine, again, you can use pip to install this, and I'm assuming that you know how to use pip if you're going to be going along in that direction. Now, as before, since we're in the notebook, we need to define, we're going to use TensorFlow version 2.x. So to do that, we're going to just, do that up here with the %sign, and then we have all of these imports, which we're going to be using throughout here. So from, future, import, absolute import, division, print function, Unicode, literals, and then obviously the big ones, so NumPy, pandas, matplotlib. We're going to be using IPython, we're going to be using TensorFlow, and yeah. So I'm actually just going to explain what some of these modules are, because I feel like some of you may actually not know. NumPy is essentially a very optimized version of arrays in Python. So what this allows us to do is lots of kind of multi-dimensional calculations. So essentially, if you have a multi-dimensional array, which we've talked about before, right, when we had, those crazy shapes like 5, 5, 5, 5, NumPy allows us to represent data in that form and then very quickly manipulate and perform operations on it. So we can do things like cross product, dot product, matrix addition, matrix subtraction, element-wise addition, subtraction, vector operations. That's what this does for us. It's pretty complex, but we're going to be using it a fair amount. Pandas. Now, what Pandas does is it's kind of a data analytics tool, I almost want to say. I don't know the formal definition of what Pandas is, but it allows us to very easily manipulate data. So, load in data sets, view data sets, cut off specific columns or cut out rows from our data sets, visualize the data sets. That's what Pandas does for us. Now, matplotlib is actually a visualization of kind of graphs and charts. So we'll use that a little bit lower when I actually graph some different aspects of our data set. The IPython display, this is just specific for this notebook. It's just to clear the output. There's nothing crazy with that. And then obviously we know what TensorFlow is. This crazy import for TensorFlow here, so compat v2 feature column as fc, we'll talk about later. But we need something called a feature column when we create a linear regression algorithm or model in TensorFlow, so we're going to use that. Okay, so now that we've gone through all that, we need to start talking about the data set that we're going to use for linear regression and for this example. Because what we're going to do is, actually create this model and start using it to predict values. So the data set that we're going to use, actually I need to read this because I forget exactly what the name of it is the Titanic data set. That's what it is. So essentially what this does is aim to predict who's going to survive or the likelihood that someone will survive being on the Titanic given a bunch of information. So what we need to do is load in this data set. Now I know this seems like a bunch of gibberish, but this is how we need to load it. So we're going to use pandas, so pd.readcsv from this URL. So what this is going to do is take this CSV file, which stands for comma separated values, and we can actually look at this if we want, I think. So it said control click. Let's see if this pops up. So let's actually download this and let's open this up ourselves and have a look at what it is in Excel. So I'm going to bring this up here. You can see that link. And this is what our data set is. So we have our columns, which just stand for, the different attributes in our data set, or the different features and labels of our data set. We have survived. So this is what we're actually going to be aiming to predict. So we're going to call this our label, right? Or our output information. So here, a 0 stands for the fact that someone did not survive, and 1 stands for the fact that someone did survive. Now, just thinking about it on your own for a second, and looking at some of the categories we have up here, can you think about why linear regression would be a good algorithm for something like this? Well, for example, if someone is a female, we can kind of assume that they're going to have a higher chance of surviving on the Titanic just because of, the way that our culture works, saving women and children first, right? And if we look through this data set, we'll see that when we see females, it's pretty rare that they don't survive. Although, as I go through, there is quite a few that didn't survive. But if we look at it compared to males, there's definitely a strong correlation that being a female results in a stronger survival rate. Now, if we look at age, right, can we think of how age might affect this? Well, I would assume if someone's way younger, they probably have a higher chance of surviving because they would be, prioritized in terms of the lifeboats or whatever it was. I don't know much about the Titanic, so I can't talk about that specifically, but I'm just trying to go through the categories and explain to you why we picked this algorithm. Now, number of siblings, that one might not be as, influential in my opinion. Parch, I don't actually remember what Parch stands for. I think it is like what... Parch, I don't know exactly what this column stands for, so unfortunately I can't tell you guys that one, but we'll talk about some more of this second. Fair, again, not exactly sure what fair stands for. I'm going to look on the TensorFlow website after this and get back to you guys. Then we have a class. So class is what class they were on the boat, right? So first class, second class, third class. So you might think someone that's in a higher class might have a higher chance of surviving. We have deck. So this is what deck they were on when it crashed. So unknown is pretty common. And then we have all these other decks. If someone got hit, if someone was standing on the deck that had the initial impact, we might assume that they would have a lower chance of survival. Embark to is where they were going, and then are they alone, yes or no? And this one, this is interesting. We're going to see, does this make an effect? If someone is alone, is that a higher chance of survival, or is that a lower chance of survival? So this is kind of interesting, and this is what I want you guys to think about, is that when we have information and data like this, we don't necessarily know what correlations there might be, but we can kind of assume there's some linear thing that we're looking for, some kind of pattern, right? Whereas if something is true, then, maybe it's more likely someone will survive. Whereas like if they're not alone, maybe it's less likely. And maybe there's no correlation whatsoever, but that's what we're going to find out as we do this model. So let me look actually on the TensorFlow website and see if I can remember what Parch and I guess what fair was. So let's go up to the top here. Again, a lot of this stuff is just straight up copied from the TensorFlow website. I've just added my own stuff to it. You can see like I just copied all of this. We're just bringing it in there. Let's see what it says about the different columns, if it gives us any exact explanations. Okay, so I couldn't find what Parch or fair stands for. For some reason, it's not on the TensorFlow website either, and I couldn't really find any information about it. If you guys know, leave a comment down below, but it's not that important. We just want to use this data to do a test. So what I've done here, if I've loaded in my data set, and notice that I've loaded a training data set and a testing data set. Now we'll talk about this more later, but this is important. I have two different data sets, one to train the model with and one to test the model with. Now kind of the basic reason we would do this is because when we test our model for accuracy to see how well it's doing, it doesn't make sense to test it on data it's already seen. It needs to see fresh data so we can make sure there's no bias and that it hasn't simply just memorized the data, that we had. Now, what I'm doing here at the bottom with this Y train and this Y eval is I'm essentially popping a column off of this data set. So if I print out the data set here, and I'm going to show you a cool trick with pandas that we can use to look at this. So I can say df train dot head. So if I look at this by just looking at the head, and we'll print this out. Oh, I might need to import some stuff above. We'll see if this works or not. Yeah, so I need to just do these imports. So let's install. And let's do these imports. I'll wait for this to run and then okay, so I've just selected TensorFlow 2.0. We're just importing this now. Should be done in 1 second. And now what we'll do is we'll print out the data frame here. So essentially what this does is load this into a pandas data frame. Now, this is a specific type of object. Now we're not going to go into this specifically, but a data frame allows us to view a lot of different aspects about the data and kind of store it in a nice form, as opposed to just loading it in and storing it in like a list or a NumPy array, which we might do if we didn't know how to use pandas. This is a really nice way to do it. Read CSV, it'll load it into a data frame object, which actually means we can reference specific columns and specific rows in the data frame. So let's run this and just have a look at it. I need to print df train.head. So let's do that. And there we go. So this is what our data frame head looks like. Now head, what that does is show us the first 5 entries in our data set, as well as show us a lot of the different columns that are in it. Now, since we have more than, we have a few different columns, it's not showing us all of them. It's just giving us the ... But we can see this is what the data frame looks like. And this is kind of the representation internally. So we have entry 0, survived 1. We have male, female, all of that. Now notice that this has the survived column, okay? Because what I'm going to do is I'm going to print the data frame head again, so df train dot head, after we run these 2 lines. Now what this line does is takes this entire survived column, so all these 0s and 1s, and removes it from this data frame, so the head data frame, and stores it in the variable y train. The reason we need to do that is because we need to separate the data we're going to be classifying from the data that is kind of our input information or our initial data set, right? So since we're looking for the survived information, we're going to put that in its own kind of variables stored here. Now we'll do the same thing for the evaluation data set, which is df evaluation or testing data. And notice that here this was train.csv and this one was eval.csv. Now these have the exact same form. They look like completely identical. It's just that, some entries we've just kind of arbitrarily split them. So we're going to have a lot of entries in this training set, and then we'll have a few in the testing set that we'll just use to do an evaluation on the model later on. So we pop them off by doing this. Pop removes and returns this column. So if I print out ytrain, or actually let's look at this one first just to show you how it's been removed, we can see that we have the survived column here. We popped, and now the survived column is removed from that data set. So that's just important to understand. Now we can print out some other stuff too. So we can look at the ytrain and see what that is, just to make sure we really understand this data. So let's look at ytrain, and you can see that we have 627 entries, and they're just, zeros or ones representing whether someone survived or whether they did not. Now the corresponding indexes in this kind of list or data frame correspond to the indexes in the testing and training data frame. What I mean by that is, entry 0 in this specific data frame corresponds to entry 0 in our ytrain variable. So if someone survived, at entry 0, it would say 1 here, right? Or in this case, entry 0 did not survive. Now, I hope that's clear. I hope I'm not confusing you with that, but I just want to show one more example to make sure. So we'll say df train 0. I'm going to print that, and then I'm going to print ytrain at index 0. Oops, if I didn't mess up my brackets, and we'll have a look at it. Okay, so I've just looked up the documentation because I totally forgot that I couldn't do that. If I want to find one specific row in my data frame, what I can do is print .loc. So I do my data frame and then .loc and then whatever index I want. So in this case, I'm locating row 0, which is this. And then on the ytrain, I'm doing the same thing. I'm locating row 0. Now what I had before, right, if I did df train and I put square brackets, inside here, what I can actually do is reference a specific column. So if I wanted to look at, say the column for age, right? So we have a column for age. What I can do is do df train age, and then I can print this out like this, and it gives me all of the different age values. So that's kind of how we use a data frame. We'll see that as we go further on. Now let's go back to the other example I had, because I just erased it, where I wanted to show you the row 0 in the data frame that's training, and then in the ytrain, output, whatever that is, so the survival. So you can see here that this is what we get from printing dftrain.loc 0, so row 0. This is all the information, and then here, this corresponds to the fact that they did not survive at row 0 because it's simply just the output is value 0. Now I know this is weird. It's saying like name 0, dtype object 0. Don't worry about that. It's just because it's trying to print it with some information. But essentially, this just means this person who was male, 22, and had 1 sibling did not survive. Okay, so let's get out of this now. We can close this and let's go to, we've pretty much already done what I've just have down here. But we can look at the data frame head. This is a little bit of a nicer output when we just have dftrain.head. We can see that we get kind of a nice outputted little graph. We've already looked at this information, so we know kind of some of the attributes of the data set. Now we want to describe the data set sometimes. What describe does is just give us some overall information. So let's have a look at it here. We can see that we have 627 entries. The mean of age is 29. The standard deviation is, 12 point whatever. And then we get the same information about all of these other different attributes. So for example, it gives us, the mean fare, the minimum fare, and just some statistics. If you guys understand this, great. If you don't, it doesn't really matter. The important thing to look at typically is just how many entries we have, as sometimes we need that information. And sometimes the mean can be helpful as well, because you can kind of get an average of like what the average value is in the data set. So if there's any bias later on, you can figure that out, but it's not crazy important. Okay, so let's have a look at the shape. So just like NumPy arrays and tensors have a shape attribute, so do data frames. So if we want to look at the shape, we can just print out dftrain.shape. We get 627 by 9, which essentially means we have 627 rows and 9 columns or 9 attributes. So yeah, that's what it says here, 627 entries, 9 features. We can interchange attributes and features. And then we can look at the head information for Y, so we can see that here, which we've already looked at before. And that gives us the name, which was survived. Okay, so now what we can actually do is make some kind of graphs about this data. Now I've just stolen this code, straight up from the TensorFlow website. I wouldn't expect you guys to do any of this, like output any of these values. But what we're going to do is create a few histograms and some plots just to look at kind of some correlations in the data, so that when we start creating this model, we have some intuition on what we might expect. So let's look at age. So this gives us a histogram of the age. So we can see that there's about 25 people that are kind of between 0 and 5. There is, maybe like 5 people that are in between 5 and 10. And then the most amount of people are kind of in between their 20s and 30s, so in the mid 20s. This is good information to know because that's going to introduce a little bit of bias into kind of our linear correlation graph, right? So just understanding, that we have like a large subset. There's some outliers here, like there's one person that's 80, right? Over here, a few people that are 70. Some important things to kind of understand before we move on to the algorithm. So let's look at the sex values now. So this is how many female and how many male. We can see that there's many more males than there is females. We can have a look at the class. So we can see if they're in first, second, or third class. Most people are in third, then followed by first and then second. And then lastly, we can look at, what is this that we're doing? Oh, the percentage survival by sex. So we can see how likely a specific person or a specific sex is to survive just by plotting this. So we can see that males have about a 20% survival rate, whereas females are all the way up to about 78%. So that's important to understand. That kind of confirms that what we were looking at before in the data set when we were exploring it. And you don't need to do this every time that you're looking at a data set, but it is good to kind of get some intuition about it. So this is what we've learned so far. The majority of passengers are in their 20s or 30s. The majority of passengers are male, they're in third class, and females have a much higher chance of survival. Kind of already knew that. All right. So training and testing data sets. Now we already kind of went through this, so I'll skim through it quickly. Essentially what we did above is load in 2 different data sets. The first data set was that training data set, which had the shape of 627 by 9. And what I'm actually going to do is create a code block here and just have a look at what was this df eval dot shape to show you how many entries we have in here. So here in our testing data set, you can see we have significantly less at 264 entries, or rows, whatever you want to call them. So that's how many things we have to actually test our model. So what we do is we use that training data to create the model and then the testing data to evaluate it and make sure that it's working properly. So these things are important. Whenever we're doing machine learning models, we typically have testing and training data. And yeah, that is pretty much it. Now I'm just going to take 1 second to copy over a lot of this code into the kind of other notebook I have just so we can see all of it at once. And then I'll be back and we'll get into actually making the model. Okay, so I've copied in some code here. I know this seems like a lot of kind of gibberish right now, but I'm going to break down line by line what all of this is doing and why we have this here. But we first need to discuss something called feature columns and the difference between categorical and numeric data. So categorical data is actually fairly common. Now, when we're looking at our data set, and actually I can open, I don't have it open in Excel anymore, but let's open this from my downloads. So let's go downloads. Where is this? Train. Okay, awesome. So we have this Excel data sheet here. And we can see what a categorical data or what categorical data is something that's not numeric. So for example, unknown, C, first, third, city, N, Y, right? So anything that has different categories, there's going to be like a specific set of different categories there could be. So for example, for age, kind of the set of values we could have for age, well, this is numeric, so that's different. But for categorical, we can have male or we could have female. And I suppose we could have other, but in this data set, we just have male and we just have female. For class, we can have first, second, third. For deck, we can have unknown, C, A, I'm sure through all the letters of the alphabet, but that is still considered categorical. Now, what do we do with categorical data? Well, we always need to transform this data into numbers somehow. So what we actually end up doing is we encode this data using an integer value. So for the example of male and female, what we might say, and this is what we're going to do in a second, is that female is represented by 0 and male is represented by 1. We do this because although it's interesting to know what the actual class is, the model doesn't care, right? Female and male, it doesn't make a difference to it. It just needs to know that those values are different or those values are the same. So rather than using strings and trying to find some way to pass that in and do math with that, we need to turn those into integers, so we turn those into 0s and 1s, right? Now for class, right? So first, second, third. You guys can probably assume what we're going to encode this with. We're going to encode it with 0, 1, 2. Now again, this doesn't necessarily need to be in order. So third could be represented by 1 and first could be represented by 2, right? It doesn't need to be in order, it doesn't matter, so long as every third has the same number, every first has the same number, and every second has the same number. And then same thing with deck, same thing with embark, and same thing with alone. Now we could have an instance where, we've encoded every single one of these values with a different value. So in the rare occasion where there's one category that's categorical and every single value in that category is different, then we will have 627 in this instance different encoding labels that are going to be numbers. That's fine, we can do that, and actually we don't really need to do that because you're going to see how TensorFlow can handle that for us. So that is categorical data. Numeric columns are pretty straightforward. They're anything that just have integer or float values already, so in this case age and fair. And yeah, so that's what we've done. We've just defined our categorical columns here and our numeric columns here. This is important because we're going to loop through them, which we're doing here, to create something called feature columns. Feature columns are nothing special. They're just what we need to feed to our linear estimator, our linear model, to actually make predictions. So kind of our steps here that we've gone through so far is import, load the data set, explore the data set, make sure we understand it, create our categorical columns and our numeric columns. So I've just hard coded these in, right? Like sex, parch, class, deck, alone, all these ones. And then same thing with the numeric columns. And then for a linear estimator, we need to create these as feature columns using some kind of advanced syntax, which we're going to look at here. So we create a blank list, which is our feature columns, which will just store our different feature columns. We loop through each feature name in the categorical columns. And what we do is we define a vocabulary, which is equal to the data frame at that feature name. So first we would start with sex, then we go n siblings, then we go parch, then we go class, and we get all of the different unique values. So that's actually what this does. .unique gets a list of all unique values from the feature column. And I can print this out. I shall print this in a different line. We'll just take this value and have a look at actually what this is, right? So if I run, I guess we'll have to run all of these in order. And then we'll create a new code block while we wait for that to happen. Let's see if we can get this installing fast enough. Run, run, run. Okay, now we go to df train and we can see this is what this looks like. So these are all the different unique values that we had in that specific feature name. Now that feature name was what? Categorical columns. Oh, what I do? Feature name. Oh, sorry, that's going to be the unique one. Let's just put, rather than feature name, let's put sex, right? And let's have a look at what this is. So we can see that the two unique values are male and female. Now I actually want to do, what is it? Embark town. And I want to see what this one is. So how many different values we have. So we'll copy that in. And we can see we have Southampton, cannot pronounce that, and then the other city is an unknown. And that is kind of how we get the unique value. So that's what that method is doing there. Let's actually delete this code block because we don't need it anymore. All right, so that's what we do. And then what we do down here is we say feature columns.append. So just add to this list the TensorFlow feature column.categorical column with vocabulary list. Now I know this is a mouthful, but this is kind of something, again, you're just going to look up when you need to use it, right? So understand that you need to make feature columns for linear regression. You don't really need to completely understand how, but you just need to know that that's something you need to do, and then you can look up the syntax and understand. So this is what this does. This is actually going to create for us a column. It's going to be in the form of a like NumPy array kind of, that has the feature name, so whatever one we've looped through, and then all of the different vocabulary associated with it. Now we need this because we just need to create this column so that we can create our model using those different columns, if that makes any sense. So our linear model needs to have, all of the different columns we're going to use. It needs to know all of the different entries that could be in that column, and it needs to know whether this is a categorical column or a numeric column. In previous examples, what we might have done is actually change the data set manually, so encoded it manually. TensorFlow just can do this for us now in TensorFlow 2.0, so we'll just use that tool. Okay, so that's what we did with these feature columns. Now for the numeric columns, it's a little bit different. It's actually easier. All we need to do is give the feature name and whatever the data type is and create a column with that. So notice we can omit this unique value because we know when it's numeric that, there could be an infinite amount of values. And then I've just printed out the feature columns. You can see what this looks like. So vocabulary list categorical column gives us the number of siblings. And then the vocabulary list is, these are all of the different encoding values that is created. And then same thing, we could go down here. Parch, these are different encodings, so they're not necessarily in order, is like what I was talking about before. Let's go to a numeric one. What do we have here? Yeah, so for a numeric column, just as this is the key, that's the shape we're expecting, and this is the data type. So that is pretty much it for actually loading these in. So now it's almost time to create the model. So what we're going to do to create the model now is talk about first the training process and training some kind of, machine learning model. Okay, so the training process. Now, the training process of our model is actually fairly simple, at least for a linear model. Now, the way that we train the model is we feed it information, right? So we feed it those data points from our data set. But how do we do that, right? Like, how do we feed that to the model? Do we just give it all at once? Well, in our case, we only have 627 rows, which isn't really that much data. Like, we can fit that in RAM in our computer, right? But what if we're training a crazy machine learning model and we have, 25 terabytes of data that we need to pass in? We can't load that into RAM. At least I don't know any RAM that's that large. So we need to find a way that we can kind of load it in what's called batches. So the way that we actually load this model is we load it in batches. Now, we don't need to understand really kind of how this process works and how batching kind of occurs. But what we do is give 32 entries at once to the model. Now, the reason we don't just feed one at a time is because that's a lot slower. We can load, a small batch size of 32. That can increase our speed dramatically, and that's kind of a lower level understanding. So I'm not going to go too far into that. Now that we understand, we kind of load it in batches, right? So we don't load it entirely all at once. We just load a specific set of kind of elements as we go. What we have is called epochs. Now, what are epochs? Well, epochs are essentially how many times the model is going to see the same data. So what might be the case, right? And when we pass the data to our model the first time, it's pretty bad. Like, it looks at the model, creates our line of best fit, but it's not great. It's not working perfectly. So we need to use something called an epoch, which means we're just going to feed the data again, but in a different order. So we'll do this multiple times so that the model will look at the data in a different way, in kind of a different form, and see the same data a few different times and pick up on patterns. Because the first time it sees a new data point, it's probably not going to have a good idea how to make a prediction for that. So if we can feed it more and more and more, then, we can get a better prediction. Now, this is where we talk about something called overfitting, though. Sometimes we can seed the data too much. We can pass too much data to our model to the point where it just straight up memorizes those data points, and it's really good at classifying for those data points, but when we pass it some new data points, like our testing data, for example, it's horrible at kind of, classifying those. So what we do to kind of prevent this from happening is we just make sure that we start with like a lower amount of epochs, and then we can work our way up and kind of incrementally change that if we need to, go higher, right? We need more epochs. So that's kind of it for epochs. Now, I will say that this training process kind of applies to all the different, machine learning models that we're going to look at. We have epochs, we have batches, we have a batch size, and now we have something called an input function. Now, this is pretty complicated. This is the code for the input function. I don't like that we need to do this, but it's necessary. So essentially what an input function is the way that we define how our data is going to be broke into epochs and into batches to feed to our model. Now, these you probably aren't ever going to really need to code like from scratch by yourself, but this is the one I've just stolen from the TensorFlow website, pretty much like everything else that's in this series. And what this does is it takes our data and encodes it in a tf.data.dataset object. Now, this is because our model needs this specific object to be able to work. It needs to see a dataset object to be able to use that data to create the model. So what we need to do is take this pandas data frame, and we need to turn it into that object. And the way we do that is with the input function. So we can see that what this is doing here, so this is make input function. We actually have a function defined inside of another function. I know this is kind of complicated for some of you guys, and what I'm actually going to do, I'm going to just copy this into the other page because I think it's easier to explain without all the text around. So let's create a new code block. Let's paste this in, and let's have a look at what this does. So actually, let me just tab down. Okay, so make input function. We have our parameters data frame, which is our pandas data frame, our label data frame, which stands for those labels, so that y train or that eval, y eval, right? We have a number of epochs, which is how many epochs we're going to do. We set that at default 10. Shuffle, which means are we going to shuffle our data and mix it up before we pass it to the model, and batch size, which is how many elements are we going to give to the model while it's training at once. Now what this does is we have an input function defined inside of this function, and we say dataset equals tensorframe.data.dataset from tensor slices dict data frame label data frame. Now what this does, and we can read the comment, create a tf.data.dataset object with the data and its label. Now I can't explain to you like how this works on a lower level, but essentially we pass a dictionary representation of our data frame, which is whatever we passed in here, and then we pass the label data frame, which is going to be, you know, all those y values, and we create this object. And that's what this line of code does. So tf.data.dataset from tensor slices, which is just what you're going to use. I mean, we can read this documentation, create a data set whose elements are slices of the given tensors. The given tensors are sliced along their first dimension. This operation preserves the structure of the input tensors, removing the first dimension of each tensor and using it as the dataset dimension. So, I mean, you guys can look at that, like read through the documentation if you want, but essentially what it does is create the dataset object for us. Now, if shuffle ds equals ds.shuffle 1000, what this does is just shuffle the dataset. You don't really need to understand more than that. And then what we do is we say dataset equals dataset.batch, the batch size, which is going to be 32, and then repeat for the number of epochs. So what this is going to do is essentially take our dataset and split it into the number of, what do I want to call it? Like blocks that are going to be passed to our model. So it can do this by knowing the batch size. It obviously knows how many elements because that's the dataset object itself, and then repeat the number of epochs. So this can figure out, you know, how many blocks do I need to split it into to feed it to my model. Now return dataset, simply from this function here, we'll return that dataset object, and then on the outside return, we actually return this function. So what this exterior function does, and I'm really just trying to break this down so you guys understand, is make an input function. It literally makes a function and returns the function object to wherever we call it from. So that's how that works. Now we have a train input function and an eval input function, and what we need to do to create these is just use this function that we've defined above. So we say make input function df train y train, so our data frame for training and our data frame for the labels of that. So we can see the comment, you know, here we will call the input function, right? And then eval train, so it's going to be the same thing except for the evaluation. We don't need to shuffle the data because we're not training it. We only need one epoch because again, we're just training it, and we'll pass the evaluation data set and the evaluation value from y. Okay, so that's it for making the input function. Now I know this is complicated, but that's the way we have to do it. And unfortunately, if you don't understand after that, there's not much more I can do. You might just have to read through some of the documentation. All right, creating the model. We are finally here. I know this has been a while, but I need to get through everything. So linear estimator. So we're going to copy this, and I'm just going to put it in here, and we'll talk about what this does. So linear underscore est equals tf.estimator.linear classifier, and we're giving it the feature columns that we created up here. So this work was not for nothing. We have this feature column, which defines, you know, what is in every single, like what should we expect for our input data. We pass that to a linear classifier object from the estimator module from TensorFlow, and then that creates the model for us. Now, this again is syntax that you don't need to memorize. You just need to understand how it works. What we're doing is creating an estimator. All of these kind of core learning algorithms use what's called estimators, which are just basic implementations of algorithms in TensorFlow. And again, pass the feature columns. That's how that works. All right, so now let's go to training the model. Okay, so I'm just going to copy this again. I know you guys think I'm just copying the code back and forth, but I'm not going to memorize the syntax. I just want to explain to you how all of this works. And again, you guys will have all this code. You can mess with it, play with it, and learn on your own that way. So to train is really easy. All we need to do is say linear est.train and then just give that input function. So that input function that we created up here, right, which was returned from make input function, like this train input function here is actually equal to a function. It's equal to a function object itself. If I were to call train underscore input function like this would actually call this function. That's how this works in Python. It's a little bit of a complicated syntax, but that's how it works. We pass that function here, and then this will use the function to grab all of the input that we need and train the model. Now, the result is going to be, rather than train, we're going to evaluate, right? And notice that we didn't store this one in a variable, but we're storing the result in a variable so that we can look at it. Now clear output is just from what we imported above, just going to clear the console output because there will be some output while we're training. And then we can print the accuracy of this model. So let's actually run this and see how this works. This will take a second, so I'll be back once this is done. Okay, so we're back and we've got a 73.8% accuracy. So essentially what we've done, right, is we've trained the model. You might have seen a bunch of output while you were doing this on your screen. And then we printed out the accuracy after evaluating the model. And this accuracy isn't very good, but for our first shot, this is okay. And we're going to talk about how to improve this in a second. Okay, so we've evaluated the data set. We stored that in result. I want to actually look at what result is, because obviously you can see we've referenced the accuracy part, like, you know, as if this was a Python dictionary. So let's run this one more time. Oh, this is going to take a second again. So, okay, so we printed out result here, and we can see that we have actually a bunch of different values. So we have accuracy, accuracy baseline, AUC, and all these different kind of statistical values. Now, these aren't really going to mean much to you guys, but I just want to show you that we do have those statistics, and to access any specific one, this is really just a dictionary object, so we can just reference the key that we want, which is what we did with accuracy. Now, notice our accuracy actually changed here. We went to 76. Now, the reason for this is, like I said, you know, our data is getting shuffled, it's getting put in a different order, and based on the order in which we see data, our model will, you know, make different predictions and be trained differently. So if we had, you know, another epoch, right, if I change epochs to say 11 or 15, our accuracy will change. Now, it might go up, it might go down. That's something we have to play with as, you know, a machine learning developer, right? That's what your goal is to get the most accurate model. Okay, so now it's time to actually use the model to make predictions. So up until this point, we've just been doing a lot of work to understand how to create the model, you know, what the model is, how we make an input function, training, testing data. I know a lot of stuff. Now, to actually use this model and like make accurate predictions with it is somewhat difficult, but I'm going to show you how. So essentially, TensorFlow models are built to make predictions on a lot of things at once. They're not great at making predictions on like one piece of data. If you just want like one passenger to make a prediction for, they're much better at working in like large batches of data. Now, you can definitely do it with one, but I'm just going to show you how we can make a prediction for every single point that's in that evaluation data set. So right now we looked at the accuracy, and the way we determined the accuracy was by essentially comparing the results that the predictions gave from our model versus what the actual results were for every single one of those passengers. And that's how we came up with an accuracy of 76%. Now, if we want to actually check and get predictions from the model and see what those actual predictions are, what we can do is use a method called .predict. So what I'm going to do is I'm going to say, I guess, result like this equals, and in this case, we're going to do the model name, which is linear est dot predict. And then inside here, what we're going to pass is that input function we use for the evaluation. So just like, you know, we need to pass an input function to actually train the model, we also need to pass an input function to make a prediction. Now, this input function could be a little bit different. We can modify this a bit if we wanted to, but to keep things simple, we use the same one for now. So what I'm going to do is just use this eval input function. So the one we've already created where we did, you know, one epoch. We don't need to shuffle because it's just the evaluation set. So inside here, we're going to do eval input function. Now, what we need to do though is convert this to a list, just because we're going to loop through it. And I'm actually going to print out this value so that we can see what it is before we go to the next step. So let's run this and have a look at what we get. Okay, so we get logistics array. We can see all these different values. So we have, you know, this array with this value. We have probabilities, this value, and this is kind of what we're getting. So we're getting logistic, all classes, like there's all this random stuff. What you hopefully should notice, and I know I'm just like whizzing through, is that we have a dictionary that represents the predictions, and I'll see if I can find the end of the dictionary here, for every single, prediction. So since we've passed, you know, 267 input data from this, you know, eval input function, what was returned to us is a list of all of these different dictionaries that represent each prediction. So what we need to do is look at each dictionary so that we can determine what the actual prediction was. So what I'm going to do is actually just do result. I wonder if I can do result 0, because this is a list, so that should mean we can index it, so we can actually look at one prediction. Okay, so this is the dictionary of one prediction. So I know this seems like a lot, but this is what we have. This is our prediction. So logistics, we get some array, we have logistic in here in this dictionary, and then we have probabilities. So what I actually want is probability. Now, since what we ended up having was a prediction of two classes, right? Either 0 or 1. We're predicting either someone survived or they didn't survive, or what their percentage should be. We can see that the percentage of survival here is actually 96%, and the percentage that it thinks that it won't survive is, 3.3%. So if we want to access this, what we need to do is click do result at some index, so whatever, one we want. So we're going to say result, and then here we're going to put probabilities. So I'm just going to print that like that, and then we can see the probabilities. So let's run this, and now we see our probabilities are 96 and 33. Now if we want the probability of survival, so I think I actually might have messed this up. I'm pretty sure the survival probability is actually the last one, whereas like the non-survival is the first one, because 0 means you didn't survive and 1 means you did survive. So that's my bad, I messed that up. So if I actually want their chance of survival, I'll index 1. So if I index 1, you see we get 3.3%, but if I wanted their chance of not surviving, I would index 0. And that makes sense because 0 is, what we're looking, like 0 represents they didn't survive, whereas 1 represents they did survive. So that's kind of how we do that. So that's how we get them. Now, if we wanted to loop through all of these, we could loop through every dictionary, and we could print every single probability of each person. And we could also look at that person's stats and then look at their probability. So let's see, the probability of surviving is, in this case, 3% or whatever it was, 3.3%. But let's look at the person that we were actually predicting on and see if that makes sense. So if I go eval, or what was it, df eval dot loc 0, we print that, and then we print the result. What we can see is that for the person who was male and 35 that had no siblings, their fare was this, they're in 3rd class, we don't know what deck they were on, and they were alone, they have a 3.3% chance of surviving. Now, if we change this, we could go like 2. Let's have a look at this second person and see what their chance of survival is. Okay, so they have a higher percent chance. So 38% chance. They're a female. They're a little bit older, so that might be a reason why their survival rate's a bit lower. And I mean, we can keep doing this and look through and see what it is, right? And if we want to get the actual value, like if this person survived or if they didn't survive, then what I can do is I can print df eval. Actually, it's not going to be eval. It's going to be y underscore eval. Yeah. And that's going to be .loc 3. Now, this will give us if they survived or not. So actually, in this case, that person did survive, but we're only predicting a 32%. So you can see that that's, represented in the fact that we only have about a 76% accuracy because this model is not perfect. And in this instance, it was pretty bad. It's saying they have a 32% chance of surviving, but they actually did survive. So maybe that should be higher, right? So we could change this number and go 4. I'm just messing around and showing you guys, how we use this. So in this one, same thing. This person survived, although, what is it? They only were given a 14% chance of survival. So anyways, that is how that works. This is how we actually make predictions and look at the predictions. You understand that now what's happening is I've converted this to a list just because this is actually a generator object, which means it's meant to just be looped through rather than just look at it with a list, but that's fine. We'll use a list. And then we can just print out, result at whatever index, probabilities, and then 1 to represent their chance of survival. Okay, so that has been it for linear regression. Now let's get into classification. So what we're going to do to create the model now